Hello, my name is Vlad Waller, and today I will talk about new features in LIRA 10.6 software package. So, we've implemented a few new types of problems in this new release. The first problem I'll be talking about is the determination of elastic and geometric properties of bar's composite cross-section. In LIRA 10.6 we've implemented the model allowing us to describe arbitrary cross-sections using material libraries and to perform the calculation of all required stiffness, plastic, inertial and reduced properties. Such cross-section can be assigned to bar elements of the model with the ability to analyze the distribution of stress across cross-section, as well as to proportion and to verify required reinforcement for RC elements. To model thin-walled fragments of cross-section, you should use two noded finite elements. For solid fragments of cross-section, use 3, 4, 6 and 8 noded finite elements. So let's take a look at it. To choose this type of problems, you need to mark a corresponding tick box at project's setup screen. Then a main view window opens where you'll create a geometry of cross-section. After geometry has been set up, you have to assign materials for cross-section fragments and also thickness of thin-walled fragments. Then you can proceed with the calculation. After the calculation is done, the program will automatically take you to the calculation results view mode, where a vast number of tables are available. There you can also visualize specific points such as center of mass, center of stiffness, center of twist, and shear center, center of neutral axis intersection. Also, the position of principal and reference inertial axis can be displayed on the screen as well as cross-section core and inertia ellipse. If the forces acting on given cross-section are set, you can visualize the diagram of normal, shear, principal or equivalent stresses for thin-walled cross-sections by any strange theory. It's also possible to display principal, normal and tangential strains. In the same way, you can set geometry of solid cross-sections. Geometry of cross-section can be modeled using finite elements or architectural elements, as it's done here. So what I'm saying is that by using polygon you can describe the shape of cross-section. Steel parts of cross-section are in blue and concrete ones are in gray. After the calculation you can display quite extensive results tables. Here how mosaics or isofields of stress are displayed when you set initial data for forces acting in given cross-section. All that I mentioned about thin-walled cross-section can be visualized for solid cross-section too. Let's now talk about properties that are determined in the process of cross-section calculation. These properties are shown in several blocks. In the first block you can check geometrical properties of cross-section obtained in principal or reference coordinate system. Reference coordinate system is the system that crosses the center of gravity and is parallel to global axis. Stiffness center and cross-sectional area are determined in global coordinate system. Moment of inertia, product of inertia and radii of gyration are determined in reference coordinate system, as well as rotation angle of principal central axis of inertia relative to reference axis. Dimensions of cross-section and perimeters can be also determined in global coordinate system. The next block shows geometrical properties obtained in a local coordinate system. It's a principal coordinate system of cross-section. In this block you can check principal moments of inertia, first moment of half-section, radii of gyration, maximum and minimum ordinates and applicates of kern distance, and dimensions of cross-section. Properties obtained in polar axes, such as polar moment of inertia, polar moment of resistance, polar radius of gyration, are also shown in this block. Next block is plastic properties. Here you can check coordinates of neutral axis intersection and plastic bending section moduli. Among torsional characteristics, there are center of twist coordinates in a local coordinate system, free torsional moment of inertia, sectorial moment of resistance. Next are shear properties such as shear center coordinates in local coordinate system, shear and shear areas, and shear section modulus. Besides that, integral stiffness characteristics and reduced material properties are obtained, as well as those characteristics that are directly involved in strength analysis. Effective elastic modulus, mean Poisson's ratio, effective shear modulus, equivalent density are also being calculated. Since cross-section can be formed from a great number of materials, it means that stiffness center and center of mass can be mismatched. As a result, quite a lot of mass inertia properties are also being obtained. All of them can be seen on this slide. After the calculation is complete, you can use a saved file to add cross-section to the cross-section library for the strength analysis. So while adding cross-section, you can specify the file in which this cross-section was created and calculated. Program will automatically display this cross-section and show all main stiffness properties obtained for it. Then it can be assigned to bar elements and you can perform a strength analysis. Since stiffness center and center of mass can mismatch, and in previous implementations of bar finite elements it was assumed that they always match, we've changed the mass of type 10 finite element, or simply put, a bar finite element. Block of additional mass inertia characteristics has been added to the initial data for numerical description of stiffness properties. They can be entered manually, thereby accounting misalignment of mass center and stiffness center. Among those properties are rotation angle of central axis of masses, coordinates of mass center in local coordinate system of the element, principal moments of inertia of masses, sectorial moments of inertia of masses. Let's now move on to the next main innovation. It's a new problem type called temperature field analysis. While working on a steady-state thermal problem, we've implemented the following: new thermophysical material properties, and new types of materials were added to material library, so you can assign them to elements of surface heat exchange. We've added new loading states and new loads, and also new finite elements. To activate a steady-state thermal problem, you have to mark a tick box that is highlighted in red. Temperature field analysis problem can be simultaneously active with problem types which are highlighted in orange. In other words, temperature field analysis problem can be used for linear, nonlinear assemblage and nonlinear assemblage problems. Arbitrary design scheme is shown on the screen, where a preset nodal temperature is assigned on the top edge. This temperature is shown as blue circles. In calculation results, you can display the distribution of temperature across design model in calculation results mode. After thermoelastic problem has been solved, you can analyze and document calculation results such as isofields of displacements, isofields of stress, principal stress, etc. And in the next block I will talk about the changes that we made to dynamic problems analysis and mainly seismic analysis. We've increased the number of natural modes that the program can determine, and because in previous versions this number was kept at 300, and we've increased it to 500 modes. If condensation of masses mode is used properly, then 300 modes are enough. However, our users kept on asking us to increase these numbers, and so we did. For dynamic plus problems, we've implemented Rayleigh damping matrix, taking into account two proportion factors, alpha and beta, for linear and nonlinear problems. In previous versions, this matrix could participate in calculation factoring in just one proportion factor alpha. But in version 10.6 we've implemented full Rayleigh matrix with the option to set these factors either in numerical form or to specify two frequencies and two logarithmic decrements based on which proportion factors will be automatically calculated. Pushover system has been expanded. In addition to previously implemented standards, we've added Ukrainian DBN and Eurocode requirements. Also, we've implemented seismic standards of Iran from 2007 and seismic standards of Republic of Kyrgyzstan from 2009. We've implemented a seismic model for calculation by three-component dynamic graphs. Using this model, you can describe almost any seismic standard that hasn't been implemented in our software yet. In other words, by setting corresponding factors that are described in a standard document, and by setting corresponding dynamic plot for all directions or for just one direction, you can describe any standard of seismic action analysis that describes spectral calculations. Due to the increase of number of countries where Eurocode is being used, we've refined the model that implements this standard. First, we've added analysis using method of shear forces. Second, we've added ability to set arbitrary graphs of dynamic factors and their coefficients. This allows us to use coefficients and graphs from national annexes. For nonlinear problems, it's now possible to obtain frequencies from natural modes for nonlinear loading history. After nonlinear analysis is finished, you can calculate arbitrary number of natural modes. To do so, you have to specify which matrix of mass will be used. The options are consistent matrix or lumped matrix. The program will automatically perform computation of oscillation modes, and they will be available in calculation results. The only restriction is that it's forbidden to use iterative, physically nonlinear finite elements. If such elements are used in analysis, then dynamic problem won't be solved. Also, let's talk about some tweaks to variation of models system. We've added to the first type of models variation that combines design combination of forces from a few topologically similar design models. This type of models variation can operate now, including unification groups, which are set in initial problems. Remember that the second type of model variation doesn't combine results in terms of design combination of forces. However, it allows us to display loading libraries for all combined problems. You can also set up different initial data for each loading state, specifically coefficients to design combination of forces, and also to perform the calculation of design combination of forces and design combination of loads for integral task that contains internal forces and displacements obtained from combined problem. Now let's move on to innovations made in graphic environment. First of all, it's worth noting that we've implemented the possibility to edit or replenish the library of materials, which is integrated into LIRA 10.6 software package. We've implemented automatic creation of design combination of loads, along with user-defined DCLs, where coefficients for each loading state have to be set manually. Now LIRA can perform the automatic creation of DCLs. Based on initial data set for design combination of loads, in this case coefficients and ties between loading states, based on initial data set for design combination of loads, in this case coefficients and ties between loading states, mutual exclusion, unification or concurrency, the program creates connectivity graph and displays it on the screen. You can modify this graph, delete some links or add your own one. This way you'll get the graph you think is correct for a given task. On the right you can set columns of design combination of forces, of loads from which the program will obtain coefficients. After you press Generate Combinations button, the program will generate automatic design combination of loads. Then they will be added to user-defined combinations, which will also be taken into account during calculation. For linear problems, we've added the option to turn off loading states from analysis. Previously, to take a look at what will happen to design combination of forces or proportion to reinforcement without some loading state, you had to delete the whole loading state and its loads, and then you had to restore them. Now you just need to disable the tick box that corresponds to this loading state, and it will be automatically excluded from the calculation. Load on an arbitrary part of plate finite element along the line or across the area has been added. It's quite difficult to set up such load manually. It's easier to set a concentrated force instead. However, this type of load was required to implement following innovations. A huge amount of work has been put into implementation of loads which are unattached to the finite element mesh. So now you can set up loads that are located somewhere in the space, and on the stage of calculation start, the program will determine on its own to which elements or which nodes this load has to be applied, and automatically calculate its intensity and determine its contour, and only then apply the load to design model. 3 types of this load has been implemented: along the line, across the area, and it also can be applied to point. To set up this load, you create some polygon and specify that this load is X across the area. So we have such design model. Surface load can be set up in 3 forms. It can be applied to plate elements, to bar elements, or to nodes of design model. Here you can see a load applied to plate elements. After the calculation has been completed, you'll see that the load was transformed. By this I mean that it now applied to those elements that completely or partially got inside its contour. The load is automatically determined accordingly to the part of the element that got into the polygon of load action. After analysis has been complete, all deformable schemes and other results become available. This load can also be applied to nodes. If this load is applied to node, then following load will affect the given design model in the following way. Loading area has been obtained for each node inside the contour of load action. Then the intensity of applied concentrated force has been calculated according to the loading area that acts on this node. Obviously, sometimes it's necessary to exclude some nodes from analysis of load application. For this purpose, a corresponding interface was implemented. You select finite elements or architectural elements, or nodes, for the matter of fact, that are not affected by load application. In this case, nodes that receive load action are highlighted in red on the screen. Loading area for each node that receive load action has been determined in the process of calculation, and load's intensity has been adjusted accordingly to its corresponding loading area. Load that can be applied to bars is another example. In the same way, you can select bar finite elements to which this load doesn't apply. You can see that in this case load has been applied to not all bar elements that got into contour of load action, but only to those that were not excluded. This is a similar load but along the line. Let's assume that we have some enclosing structure that we want to present as a load. After the calculation, we can see that those plate elements that got inside the load action area was found, as well as load value for each of those finite elements. There is similar load which is applied to point. You can specify location of load application in global coordinate system, its intensity and direction. The program will determine on its own to which element this load will apply during calculation. All previously described loads significantly save time when setting loads and editing them. Before, even small changes led to necessity of additional editing of huge amount of elements. For example, you've locally changed finite element mesh, and now you have to consider that it's also necessary to set up load on new elements, which can be involved in several loading states. You have to remember and control all those details. Now the process is so much easier. One more innovation involving loads is glaze ice load. Previously we've implemented interactive load, which is dead weight. Now we've added glaze ice to interactive loads. Now when setting glaze load, you have to specify building standard according to which glaze ice load shall be summed, specify the zero coordinate of a design model relative to the ground surface, and thickness of glaze ice. If frosting is partial, it's necessary to set its perimeter. If frosting is present on the whole perimeter of cross-section, the program will calculate the outer perimeter of cross-section on its own and automatically determine glaze load parameters and apply it to the design model. Obviously, the position of elements in space is taken into account. If coordinates of elements change, the program will automatically recalculate all parameters of the load. So after you apply these loads, you don't have to track it anymore. It's now possible to add description for architectural and finite elements that can be turned on when required, and they can be visualized on design model. Now you can easily add legends to design scheme. To do so, you have to previously set the description for element and turn it on when needed. We've also added the model control mode. On the left there is a list of control indicators. Each determines control scheme that is implemented in program's algorithm. After design model is created, you can run certain tests based on which the whole design model will be controlled, and control protocol will appear on the screen. In case of a mistake, the red sign will appear. In case of a warning, there will be a yellow one. In this case, we have a warning about similar cross-sections in design scheme. This means that absolutely identical by their parameters cross-sections have different names. Probably there was a typo made somewhere when setting a cross-section. The next innovation addresses architectural elements. When setting triangulation step for architectural plate, you can set the checkmark that activates the option of generating a rigid body in places of bar elements junction. Rigid body will be created automatically along the contour of bar elements cross-section during triangulation of such architectural plate. You can see that parametric cross-sections adjoined to the plate are highlighted with a clear-cut contour. As for steel cross-section, rigid body is described by lines in the form of given cross-section. You can now visualize stress on extreme fibers of plate elements along alignment axis in calculation results for separate loading states as well as for design combination of loads. Previously it was possible to visualize either forces or principal stress on extreme fibers. Sometimes we need to take a look at stress on extreme fiber along some direction, so we've implemented this option. In similar way, we've implemented a calculation and visualization of extreme normal stress and strain in cross-sections of bar elements caused by loading states, DCLs and DCFs. In each cross-section of bar element, internal forces will be determined first, and then, according to these internal forces, the distribution of normal stress across entire cross-section will be calculated. Then points where this stress are extreme, I mean minimum or maximum, will be selected. Then diagram of extreme stress is constructed. Of course, in the same way you can generate tables of extreme stress values and their coordinates. It's easy to check calculation accuracy. Passage through all design combination of forces is being performed. As for design combination of loads, passage through all points of cross-section is being performed to find extreme value. Capabilities of the scale have been significantly expanded. The scale became more interactive. This means that if you bring over mouse pointer to the scale during visualization of some calculation result and hold it for a few seconds, the scale will go to the constructor mode and additional tools will appear. By clicking on the cross, you can turn off visualization of such color. Color of turned off ranges can be set in scale settings. By clicking on color fragments of the scale, you can perform selection of those elements or nodes in which the value presented in given range was determined. We've expanded capabilities of scale for reinforcement. There's a new feature allowing you to set background reinforcement. Aside from setting step and diameter where main reinforcement will be automatically recalculated, you can add the value of background reinforcement with other step and diameter. The program will automatically account this background reinforcement to build the scale. Also, you can fill in a numeric description of reinforcement scale and set it by formulas or etc. We've also added the ability to calculate the center of stiffness and center of mass of the whole design model or its separate part. Also, you can calculate directions of maximum and minimum stiffness. Corresponding information will be displayed in the modes window and visualized on the screen. For laws which describe the creep process, it's possible to calculate parameters based on preset initial data. If you perform a physically nonlinear calculation factoring in creep, then you can calculate the creep diagram not manually but automatically using Eurocode theory. To do so, you need to set area of cross-section, perimeter, humidity, start and end time of its action. You can calculate such a diagram for the 44th law, for the 41st law. Two parameters that participate in strange analysis are being calculated. You can now make not only static images but dynamic ones as well. Aside from images that are saved on the hard drive, now certain information is being saved to the project file. If design model had some changes in geometry or in loads, then with just one click after calculation you can regenerate one or all files formed as dynamic pictures. Also, I want to introduce you to some more minor changes. In status bar, there's now a quick access toolbar to properties of projection presentation. We've also refined algorithm of pivot point determination. Construction axis, design grid, elevation indicators, etc. Aren't taken into account when you rotate scheme using mouse now. Rectangular grid was added to coordinate grid with the possibility to set different steps along the axis. We've optimized performance during operations with large design models made of solid finite elements. Previously, rendering of such model took a lot of time. We've optimized this process. You can also now set the step of modes and displacements animation. For time-dependent dynamics problems, you can set the step of for animation and coefficients for animation of modes. Base node is now factored in plots of dynamic plus system, and relative to this base node, the plot is being displayed. We've also implemented import of loading state library from previously created projects. Orientation filters for bar elements has been added to select objects mode. Recognition of solid finite elements has been added to fragmentation of elements mode. Automatic setting of alignment axis for bars and solids along global axis was implemented. Alignment rule used now if nothing has been set. After you've created plate or solid finite element, even if you haven't set up alignment of axis in corresponding mode, axis will be aligned by some rule anyway. And for most cases that should be enough. We've added the concept of default cross-section material structural design parameter. It will be automatically assigned to new elements. For structural elements, there's now implemented ability to display diagrams of extreme values for the whole element in results for steel structures mode. Previously, the diagram has been displayed with all values that were calculated. Now you can leave just extreme value if needed. In model analysis mode, we've added search of matching nodes and elements. And we've increased the number of loading states for design combination of forces from 96 to 300. And the last, for all types of finite elements, we've added calculation and display of strain energy density for loading states and design combination of loads. The next block describes innovations which address converters and interactions with other software. Capabilities of import from Revit 2016 has been enhanced. Since Revit now has new types of loads that couldn't be imported into LIRA before, now converter has been widened and these loads are taken into account. Also, we've added converter with Revit 2017. To make possible import and export of design models between programs. We've implemented import of design models from Tekla Structure 21. So you can now exchange design models between LIRA and Tekla. We've also implemented import-export in transitional format named SLI, as well as export of proportioned reinforcement in plate elements for all plan through transitional format ISF. We've enhanced import of floor plans from DXF format and import of design models from IFC format. And also we've added converter with Plexis through LIRA API model. Let's move on to innovations implemented in soil system. First of all, I have to say about new capabilities to perform calculation, automatic calculation of stiffness properties of piles. All 6 characteristics are calculated at the same time. We've implemented such capability for single piles, pile clusters and artificial foundations. After boreholes are set in soil system and program has automatically built 3D model of soil body, it can be exported into solid finite elements that can then participate in strange analysis. I will briefly tell about innovations for reinforced concrete structures in 10.6 version. You can now use non-metallic reinforcement for calculation based on Russian SP. It's also possible now to use Eurocode 2, taking into account national annexes of Republic of Belarus and Republic of Kazakhstan. Corresponding standards are now in drop-down list of available standards when you set initial data for reinforced concrete design. You can now build a bearing capacity surface for preset reinforcement and proportioned reinforcement in bar finite elements. Punch and shear analysis has been significantly enhanced. We've added accounting of relief forces and capitals. Punch and shear analysis was also implemented in problems of assemblage system. Absolutely rigid bodies are now taken into account also. And we've improved the algorithm of automatic creation of punch and shear contours. It's now possible to proportion and test reinforcement for cross-sections that were created as arbitrary cross-section. You can create random cross-section and specify in initial data location of reinforcement in this cross-section. Then set limits, initial and final value of reinforcement area. The program can perform checking of specified areas or perform proportion of required reinforcement for such cross-section. For plate elements, we've added accounting of buckling and implemented wood armor theory of reinforcements proportion. Now it's possible to manage the accuracy of calculation during reinforcement proportioning for plate and bar elements. Using this slider that is highlighted in red, you can set required balance between speed and accuracy of calculation. Now, briefly we'll talk about innovations in steel structure section. We've added a few hollow sections. You can see the list of these cross sections on the screen. It's now possible to perform analysis of elements taking into account corrosion. You can set a corrosion wear in millimeters or as a percentage. The program will automatically correct cross-section form and recalculate all stiffness properties. After that, new stiffness properties will be accounted in strange analysis. Also, a new form of cross-section will be analyzed. Therefore, all points where stress would be checked will be determined in places where there is steel, in fact. Also, we've created an application to determine effective lengths of a bar element. It performs calculation of effective lengths based on initial data and according to standards and reference literature. And also we've updated calculation based on dBn up to dBn from 2014. Constraint torsion is now taken into account in strength analysis of the seventh type of finite element. B moments are added to formulas of stress calculation. Accounting for additional condition of use factor for elements of truss web made of pair angles has been added. Also, accounting for additional condition of use factor has been added for seismic analysis. Proportioning and checking of ropes has been refined. Also, we've implemented automatic determination of rolled steel type. Now you don't have to specify the type of rolled steel manually. And the last, we've also expanded the database of steel gauges and steel grades. So it seems that I finished this brief rundown of main innovations and changes in LIRA 10.6. Thank you for your time and attention, and till the next time.